Welcome dear children to today's session in physics. Today we are going to discuss what happens when a dipole is kept in a uniform electric field. Consider a dipole kept in a uniform electric field. You know how to represent a uniform electric field. Uniform electric field is characterized by a set of equidistant parallel lines. So these field lines represents a uniform electric field, and a dipole is kept in a uniform electric field. So we show a dipole. So here you have negative charge and here the positive charge. So this represents a dipole which is kept in an external uniform electric field. So what happens when a dipole is kept like this? That's what we are discussing. Since the electric field is a uniform electric field, the force experienced by the two charges plus q and minus q. So this plus q will be experiencing a force in the direction of external electric field, and this charge negative q will be experiencing a force in the opposite direction of electric field. So this is the force QE, and here also the force is QE, where Q is the charge and E is the magnitude of electric field. So these two charges, they experience force, and these forces are in opposite direction. So what about the net force? The net force acting on the dipole will be equal to 0, because plus QE and minus Q, that means QE and QE, they are acting in opposite directions on the dipole itself. So the net force experienced by the dipole will be equal to 0. Now we can see that the two forces, their lines of force do not coincide. The lines of action of these two forces plus QE and this minus QE, those two lines of action do not coincide. Because of that, these two equal and opposite forces, we can say these two equal and opposite forces constitute a couple. These two forces constitute a couple, which in turn produces a torque. So this is what is happening when a dipole is kept in an external uniform electric field. That means the two equal and opposite forces, since their lines of action do not coincide, these two forces constitute a couple, which in turn produces a torque. And you know, the torque produces rotation. That rotation we will discuss later. Let's first find what is the net torque acting on this dipole. So the torque due to a couple, we know torque is equal to, the expression for torque is equal to one of the forces into, so two equal and opposite forces. Here the forces are QE and QE acting in opposite direction. One of the forces into perpendicular distance between the two. Perpendicular distance between the lines of action of the two forces. So one of the forces into perpendicular distance between the lines of action of the two forces will give you the expression for torque. So let's find what is that perpendicular distance. So to find perpendicular distance, we do the construction like this. That is, we have to find the perpendicular distance between the lines of action. So this is one line of action, this is the other line of action, and this is the perpendicular distance between the two. So if we call these points as A, B and C in the diagram, this perpendicular distance is AC. So we can write it as QE into perpendicular distance from the diagram, it is AC. Now let's find what is this AC. So to find AC, before finding AC, we define an angle. So here you have negative Q, here you have positive Q. So you know, for the dipole, its dipole moment is directed from negative charge to positive charge. So this is the direction of dipole moment. from negative to positive or from B to A. Now that dipole moment, let it makes an angle theta with the electric field. So here theta is the angle between dipole moment and electric field. Theta is the angle between dipole moment and electric field. So if I write theta, here also I can write theta. So in the right triangle, so ABC is a right triangle. In using the trigonometric identity, you can find AC, what is the perpendicular distance. That's what we want. So what will be AC? So AC from figure, we can write sin theta is equal to, sin theta is, so sin theta equal to AC divided by AB. AC divided by AB. It is this AC what we want. So AC equal to what? AB sin theta. AC is equal to AB sin theta. Now you look, what is AB? AB is dipole length, length of the dipole. What about the length of the dipole? AB, the length of the dipole is 2A. We were writing length of the dipole as 2A. So in short, AC is equal to 2A sin theta. AC is equal to 2A sin theta. So the expression for torque becomes QE into 2A sin theta. Now rearranging this as 2AQ into E sin theta. So 2AQ, you know what is 2AQ? 2AQ is dipole moment. So P, replacing 2AQ with the P, we have PE sin theta. So the torque tau is equal to, tau is the representation for the torque tau equal to PE sin theta. So this is the expression for magnitude of the torque produced when a dipole is kept in an external electric field. Now you know the torque is a vector quantity and dipole moment is a vector quantity, electric field also is a vector quantity. So this equation we can write in vector form. So when we write it in vector form, it becomes vector tau is equal to vector P cross vector E, because here the product is in terms of sin theta. So that comes as what? Cross product. That means torque tau equal to P cross E. So this is the expression for torque produced when a dipole is kept in an external electric field. So very important expression and derivation. And it is a frequently asked question also for the board exam. So what we mean by this torque? So the dipole is experiencing a torque means it will rotate in the presence of external uniform electric field till it get aligned in the direction of external field. That's what is happening. So whenever a dipole is kept in an external electric field, depending on this theta, so torque depends on that theta, the angle of theta, that angle theta, which is the angle between dipole moment and electric field. If this theta is 0 or if theta equal to 180 degree, this torque will be equal to 0. So it will not rotate. So for any other angle other than 0 and 180 degree, the dipole will experience a torque and it will rotate. That's what happens when a dipole is kept in an external electric field. So equilibrium positions are of two angles. That means we have the equilibrium positions of the dipole when theta equal to 0 degree and theta equal to 180 degree. The reason is torque will be equal to 0. So when torque is equal to 0, the dipole is said to be in equilibrium. Okay, and theta equal to 0 and theta equal to 180 degree are the positions of equilibrium. And these two positions of equilibrium, they are called as stable and unstable equilibrium. Theta equal to 0 degree is termed as stable equilibrium and theta equal to 180 degree is called as unstable equilibrium. Why they are called stable and unstable, that we will be discussing in the next chapter. Okay, so for time being, try to understand that the angular orientation theta equal to 0 is called stable equilibrium and theta equal to 180 degree is called unstable equilibrium. So this shows the orientation of the dipole in stable equilibrium. That means the dipole moment P and the electric field E are in the same direction. So theta equal to 0. Okay, and this shows the orientation of the dipole in an unstable equilibrium because P is in this direction, that means from right to left, and electric field is in left to right direction. So here theta equal to 180 degree and the dipole is said to be in unstable equilibrium. So this is what we mean by stable and unstable equilibrium. Now, the dipole is said to be not in equilibrium with the electric field when it experiences maximum torque. So, you know from the expression, because torque is P sin theta, so that torque will be maximum when sin theta is maximum. Maximum value of sin theta, you know sin theta equal to 1. That is the maximum value of sin theta. So, the sin theta is equal to 1, that is possible when theta equal to 90 degree. So, torque experienced by the dipole is maximum when theta equal to 90 degree. So, maximum torque is given by PE. So, when theta equal to 90 degree, the dipole experiences maximum torque and it is said to be not in equilibrium with the electric field. So, this shows the orientation of the dipole when it is not in equilibrium with the electric field, and here the angle is 90 degree. So, when the dipole is kept in an external uniform electric field, it experiences a torque and it rotates. That is the conclusion, and the expression for torque is P cross E, or the magnitude of the torque is PE sin theta, and we have the positions of stable, unstable equilibrium, and we know when will we say the dipole is not in equilibrium. This is what we discussed. Now we consider the case when a dipole is kept in a non-uniform external electric field. So when a dipole is kept in a non-uniform external electric field, it is sure that it will experience a net force, because when a dipole is kept in an uniform electric field, we have net force to be equal to 0, because it was experiencing net force 0 because both the charges were experiencing same force. But in this case, when we keep it in an external non-uniform electric field, so electric field is not uniform and the two charges of the dipole will not experience same force. So that is the case. So when in a non-uniform external electric field, when a dipole is kept, it will experience a net force. Torque will be there, along with that net force will not be equal to 0. So here we are considering a simplest case in which torque is equal to 0. That means theta equal to either 0 degree or 180 degree. In such cases, when dipole is kept in a non-uniform electric field, what about the direction of the force experienced by the dipoles? That thing we are discussing now. So we consider an electric field as shown, that is from left to right, and the dipole is kept in the electric field with its dipole moment in the direction of electric field. And here one more thing is here, that is electric field is not uniform electric field. It's given in this direction, field is increasing. So from left to right, field is increasing. So the magnitude of electric field here, it will be comparatively less with that of electric field on the right side, or on the right side electric field, the magnitude of electric field will be more, because we are considering non-uniform electric field and it is given in this direction, field is increasing. So in that field only this dipole is kept. So the force on the positive charge will be more than the force on the negative charge. So force experienced by the positive charge will be more than the force experienced by the negative charge. We know the force experienced by the positive charge is in this direction and the force experienced by the negative charge is in the opposite direction. And these two forces will not get cancelled because they are not equal in magnitude. So there will be a net force, and in which direction the net force will be, because the force acting on the positive charge is more in magnitude. So net force will be acting in this direction. That means in the direction of dipole moment, the net force will be acting on the dipole and the dipole will be moving in that direction. So dipole moves in this direction because it experiences net force in this direction and hence it moves in that direction. Now we consider another case, that means a dipole is kept in an electric field with the same type of electric field. That means in this direction from left to right the field is increasing and the dipole is kept with its dipole moment in opposite direction. So just opposite to the previous situation. So what about the case here? So here also the field is increasing in this direction. So here what happens is positive charge will experience a less force compared to the force experienced by the negative charge, because this side electric field is more. So the force experienced by the positive charge is in the direction of electric field and that experienced by the negative charge in the opposite direction. But this force is more in magnitude compared to this force. So net force acting on the dipole will be in this direction. So this is the direction of net force, because negative charge experience a force in this direction opposite to the direction of electric field, and that force is more because this side the field is more. So net force acting on the dipole will be in this direction and hence the dipole will be moving in this direction. So in what is the direction of net force? In that direction the dipole will be moving. When a dipole is kept in an external non-uniform electric field, the dipole may experience both net force and net torque. So if we are assuming the dipole to be in the torque 0 position, that means when theta equal to 0 or theta equal to 180 degree, either the dipole can experience a force in the direction, that means in both the case the dipole will experience a force in the direction of dipole moment. Here the net force is in the direction of dipole moment. Here also the net force is in the direction of dipole moment. In both the case the dipole experiences a net force in the direction of dipole moment. See, this has got an important application in the small experiment what we used to do in lower classes. That means rubbing your scale on the dry hair, non-oily hair, and showing that scale to small bits of paper. We have seen that this scale attracts that bits of paper. So this we can explain on the basis of this dipole in non-uniform external field. So you know, by rubbing the scale on non-oily dry hair, what happens is by friction, you know, we have already studied frictional electricity. By friction this scale will attain a charge. So suppose the scale attains a negative charge. By rubbing the scale gains some electrons and it attains a negative charge. When we show this scale nearer to small bits of paper, so these are bits of paper. So when we show the scale which has got frictional electricity nearer to this small bits of paper, this small bits of paper will get polarized. What do you mean by polarization? By the method of induction. This negatively charged scale will induce a charge on this paper bit. So negative charge, no, so this side it will be positive. So I will show in big one. So this side it will be positive and this side it will be negative. By induction this bits of paper attains there is a local movement of charge within that bit of paper. So positive charge will get attracted towards this negatively charged scale or comb, and negative charge in the opposite direction. So there is a displacement of positive and negative charges in that bit of paper. Or we can say that that bit of paper has become a dipole now, because equal amount of positive and negative charge is there. So that positive and negative charge separated by a small distance, that's what we call as dipole. Now, where is this dipole? The dipole is in the electric field produced by this charged comb or charged scale. Okay, so this dipole, now it is an induced dipole, let it be. That dipole is in the electric field produced by this charged scale or comb. And what about the electric field produced by the comb? We know the electric field produced by the comb is not a uniform electric field. As we go away from the comb, the field will be decreasing. The strength of the field or the magnitude of the field will be decreasing. The direction of electric field is towards the negative charge. This is the direction of electric field. Electric field is in this direction. So this is the direction of electric field, and in that direction the field is increasing, because as we go away from the comb or the scale, the field will be decreasing. So towards the comb the field increases, and that is the direction of electric field because it is a negatively charged comb. So this is the direction of increasing electric field, and that is the direction of dipole moment also. Dipole moment is in this direction. So in such a case, we know the net force experienced by the dipole will be in the direction of dipole moment. That means in the direction of dipole moment means in this direction. In this direction, this paper bit experiences a net force, means this paper bit is getting attracted towards the charged comb or charged scale. This is what is happening. So when we show that rubbed scale or rubbed comb towards the bits of paper, this is what is happening. First of all, by the method of induction, that bits of paper becomes dipoles, and in the case of that dipoles, they are kept in a non-uniform electric field, and in that non-uniform electric field they experiences a net force in a direction that is towards the comb or towards the scale. That is how they show that attraction. So with that we conclude today's session, and what we discussed today is a very important topic as far as board exam is concerned. Study well. Thank you.